Okay, now you have completed your first really big, serious astrophotography project in the optical. And hopefully it was fun. Hopefully you made something pretty, but it's more than that. It's more than just a pretty picture. There is a ton of physically interesting and important information in your picture if you know how to read it. And in this video, I'm going to show you how to extract physical information like the size of the region, the temperatures of the gas and the surrounding dust. And I'm going to show you how to use that to calculate other physically interesting quantities, such as the density, both in the region and surrounding. So there's a lot going on in your image. You have many layers, but these layers can be put into three categories. You have the stellar layer. The LRGB combination is the stellar layer, and it focuses on the stars. So in this image, we see there's a whole bunch of stars, really bright, massive, hot stars that are driving everything that's going on in the image. Though in some star-forming regions, may all be driven by a single star. Or in others, like the Tarantula Nebula up in the Large Magellanic Cloud, that star-forming region is bigger than anything in the Milky Way galaxy. It's huge. And so there's going to be a spectrum, small ones to big ones. Then you have your narrowband layers, H alpha, O3, S2. And this is gas, but it's not just any gas. It is gas that's been heated by these stars. These same stars, they heat the surrounding gas, ionize it. And these different elements, when ionized in this way, they emit light at different temperatures. So using what you've observed, you can figure out temperatures from this interior region, this region that's been heated and ionized by these stars. And then you have the mid-infrared layers from Spitzer or Weiss. It's going much farther out in wavelength, partway to the radio. And what that shows is the surrounding dust. In your optical only image, you're probably going to see some dark surrounding regions, but once you throw in that mid-infrared, they glow because those stars are not only heating and ionizing the gas, but surrounding this gas is much denser material, the material out of which the stars formed. And the stars also heat that denser material, that gas in the embedded dust, and the dust then radiates in the mid-infrared. And we can use that to figure out the temperature of that surrounding material. So lots of stuff we can extract here. And then we're going to use these temperatures and other information to calculate densities. So let's start with the density in the interior. Then we'll move on to the density of the surrounding gas out of which it all formed. Let's start with the density on the inside. So I'm going to go to the dot cam. I'm going to do some written notes for you. Okay. So all these star-forming regions start with stars. So there we have some stars. But the only stars that really matter for setting up the region, heating and ionizing the gas, are the O stars and the B stars. These are your most massive stars, particularly the O stars. They're the most massive, they're the hottest. They put out the most ionizing ultraviolet radiation. B stars are a little bit lower mass, less temperature, and they put out a little bit. So the O and the B stars, they make UV radiation, and some of that will be greater than 13.6 electron volts. And that's the energy of photon that you need to ionize hydrogen. You may remember that number from high school chemistry. Most of the surrounding gas, most of the gas in the universe is hydrogen. Very simple. A proton with an electron in an orbital around it, at least in its neutral form. Proton and electron together. But you dump 13.6 eV photon in there, and it can kick out the electron and ionize it. So O stars and B stars are spitting out a lot of ionizing ultraviolet photons. I'll just put this back up. We've seen it a couple times now. This is the Planck spectrum, the black body spectrum, the thermal spectrum for stars of different temperatures. So way up here, we have the ultraviolet. Here's the visible band. Here's the infrared going down to the mid-infrared and then eventually far and the radio. And the hottest stars, they peak up here. They're stars even hotter than the ones in this diagram. They peak up here in the ultraviolet, and then you have the exponential turnover that we see in all these curves. But the hot ones spit out a lot of radiation, ultraviolet light above 13.6 eV, and that can ionize the surrounding gas. Once you get down to the B stars, it spits out less, a lot less, of that ionizing radiation. And once you get beyond that, they don't spit out anything that makes a difference. Okay. So we have these stars. They're spitting out ultraviolet radiation. Right there, this is UV, creating a region. Okay, and we call this an H2 region. And out here, this is called H1. Okay, just to remind you, H1 means neutral hydrogen. You have a proton, and then in an orbital around it, you have an electron. The proton's positively charged, the electron's negatively charged, and it's atomic. Actually, out here, as we'll see, it's cold enough that the atoms, the hydrogen atoms bond up. They like to pair up, and you have what we call molecular hydrogen, two hydrogen atoms together. The point is the electrons are bound to the protons out here. That's the H1 region. And here, because of those ionizing photons, the protons and the electrons are separate. And they're just whizzing around in all sorts of trajectories. Okay. Now, these stars, these hot O stars and B stars, they keep pumping out this UV radiation. So you may think that this region will just get bigger and bigger and bigger to no end. But that's not true. The protons and electrons, they want to come back together. They want to recombine, particularly out here in the outskirts. That UV light from the stars all the way over here has been spread thin, and it's less able to ionize because of that. And they naturally want to recombine, so at some point, recombination wins. So the size of the region is set by the condition that the ionization rate equals the recombination rate. When those two are in balance, that's when we have a well-defined boundary. Okay, now those are words. I'm going to slowly turn this into symbols, an equation. So for ionization rate, let's call that N star. It's the rate of UV photons above 13.6 EV coming out of all the stars in there. And I'll show you how to estimate that in a little bit. The recombination rate is going to depend on a couple things. It's going to depend on the number of protons. And the ionization rate is number of photons per second. So on the right, it's going to be the number of recombinations per second, matching that ionization rate. And to recombine, you need to have a proton, so it's going to depend on the number of protons. And then by that, you multiply the rate of encounters, let's say rate of encountering electrons and recombining. So we're taking it in steps. First, you have to have a proton, and then you have to encounter an electron, which will happen at some rate, and then the encounter needs to lead to a recombination. So let's fill in more of this here. We have N star, number of protons. That's going to be the density of protons, number density, number per unit volume times the volume. So number of protons, it's right here. Number density of protons times the volume. Now, I didn't use P, I used H+. That's hydrogen once ionized. And if you ionize hydrogen once, you have a bare proton. So that's just another way of saying proton. Okay. Now, the rate of encountering electrons and recombining with them, well, it's going to depend on the density of electrons. The electrons are more dense, you're more likely to encounter them. And when you do encounter them, there's going to be some probability of recombination. Now, that's something that can be calculated from quantum mechanics. We won't do that here. We just look that up. But it's basically a function of temperature. The hotter the gas is, the electrons and protons are moving faster, and it's harder for them to recombine. The lower the temperature, the slower the motion, the easier the recombination. So I'm just going to rewrite this, rearranging some terms. Let's put alpha of T out front. Proton density, electron density, and the volume. Now, the density of protons on the inside and the density of electrons on the inside. How do you think those are related? Before the stars turned on, it was all neutral hydrogen gas in there. Now it's ionized. It's in the same volume. And so these densities have to be the same because for every proton, there's just one electron. Every electron, there's one proton. So these densities, the proton density, the electron density in here, they have to be the same. We can simplify this. Alpha of T times the proton density squared. They're the same, so just treat as NH, square it, since there are two of them, times the volume. Okay. Now, as I said, alpha of T, we can look this up, and we'll look it up for T of 10 to the 4 Kelvin, which is typical of these regions. As we'll see, the interior temperatures around 10,000 Kelvin, plus or minus. So we look that up right there. And for the volume, we're going to make an approximation. These regions are messy. I'll just show you again. It's messy. We have protrusions and bumps and lumps, but we're going to do a very astronomer, very theorist thing. We're going to approximate that ionized region as a sphere. Volume of a sphere, you may recall, is 4/3 pi r cubed. This calculation is not going to be super precise, super exact. We have some bumpy, lumpy region, but it's still roughly spherical. At least close enough to it for the accuracy of this calculation. So we plug that in here, look this up, plug it in here. We'll figure out a way to determine the rate of ionizing photons. And so what we're solving for is the density, the interior proton density. And I'll skip the algebraic steps. I'll just give it to you. NH plus, the proton density in the inside, is 540 per cubic centimeter. I haven't mentioned this before, astronomers are old school. You all use MKS. Astronomers, many of us still use CGS from like 100 years ago. Instead of meters, we use centimeters. Instead of kilograms, we use grams. We use seconds, same as everyone else. Then we multiply this by, we're going to have n star. Here I have it in units of 10 to the 49 per second. There's going to be an exponent of 1/2. Now, when you're calculating with this equation, if you're not used to fractional exponents, it's easy to make a calculator error with fractional exponents. So you may just want to raise this to the 0.5. Save yourself some potential problems. And lastly, we have the radius. When you solve it, do some unit substitutions. You get r sub s measured in parsecs to the -3/2. Again, for calculator reasons, you may just want to raise that to the -1.5. Now, why the S? The S stands for Stromgren. What we've done here is something called the Stromgren sphere approximation. Okay. I guess Stromgren was the first person to do it. Okay, so to do this, we need to figure out the size of our region and the number of ionizing photons. Now there's a table, let me show that to you, linked in the lab, or linked in the module guide. And this is my students just did this in class today, so it's full of numbers. The one you'll encounter will be cleared out, but put your team name there, your target, and these are the things, these are the things we're going to calculate. We're going to start with the Stromgren radius in degrees. Then we're going to convert it into parsecs using the distance. Then we're going to figure out the ionizing flux, that's the n star. And then we'll calculate the interior density. That's our first calculation. And all this is for the outside density. So the Stromgren radius, how do you do it? There are two ways. And the notes are over here. If your whole image, well, if the whole region fit in your image, you can do this in Afterglow. I'll show you. I'll come here to Afterglow. I'll come down to the measuring tool. Click on the center of the stellar region that's ionizing. And then we want to draw a line out to the wall. Now, don't worry about protrusions and things. Go back to kind of the base wall. Maybe somewhere along here or here. These regions are not perfect spheres. So just kind of eyeball something that works approximately. Maybe something like that. Come down here and say that's 8 arc minutes. And we're going to want to get that in degrees. So to go from arc minutes to degrees, you divide by 60. That's right here. So if you're measuring in Afterglow, you get the Stromgren radius in arc minutes, divide by 60. That's in degrees, and that's what you're going to put in this column. Now, it could be that your region was bigger than your image, in which case you can go to Stellarium. I think I'm going to close this out and just reload it so you can see how to do it from scratch. Load up Stellarium. Here we go. Turn off the ground and turn off the sky. I'm going to search for my object. Mine is M16, the Eagle Nebula. Maybe I'll put it in equatorial coordinates so it matches my image. Let's zoom in and find it here. There it is. It's a pretty big region. Here's the central stars. So my region was only this big, and here's the central cavity right here. So what you can do is get the top of the cavity on the top of the page and the bottom of the cavity on the bottom of the page. Adjust it. Something reasonable. If you can only see it left-right, figure out what the left-right distance is and kind of make that the up-down distance from the center and the up-down distance from the top to the center. And then you can read off the field of view. I got 0.2 degrees, and that's the diameter. So you divide that in two, it's about 0.1 degrees. And that's another way to measure this. F11 to shrink it down. You can see here, if you're doing stellarium, you line up the diameter of the region along the vertical. The field of view is the vertical diameter, so divide it by 2 to get the radius. And that's what you can stick over here. Okay, so you now know the radius in angle. Any image is an angle on the sky. To turn it into a physical distance, we need to know how far away your target is. So in that case, you just Google the target. I haven't done this, but let's give it a try. Eagle, nebula, maybe go to Wikipedia. And you can get a distance. Here it is. And we want the distance in parsecs. So this one is 1,740 parsecs away. And that goes in here. Now, yeah, we just pulled that out of Wikipedia. Where did it come from? It came from Gaia. Just like in Module 2, all of our stars, we got the Gaia distance for it. Gaia has given us the distance to these stars as well. So that's where that comes from. Okay, so you have the distance to the nebula, you have the angular size of the nebula. So using the small angle equation, you can calculate the physical size of the nebula in parsecs, which is what we need to use this equation. We need the physical size of the nebula in parsecs. Here's the small equation. Take your radius in degrees, divide by 180 degrees, multiply by pi to get into radians, and then just multiply by that distance in parsecs, which we just looked up. That will give you the size of the region in parsecs. So you can see my students, they did a whole bunch of star-forming regions. They're at all sorts of different distances. Some are fairly close. Some, like the tarantula, very, very far away, out in the Large Magellanic Cloud, not even in our galaxy proper. And then they calculate the Stromgren radius. And these tend to be a few parsecs, though some can be bigger. You can have some that are tens of parsecs. And some can be small, like Demarin's object. It's near the Orion Nebula. It's just a little B star that's heating up that whole region. It's not very big. So it's a fraction of a parsec. But most will be a few parsecs. Here's Tarantula. It's a huge region. If you're doing the Tarantula Nebula, you may choose to do just a pocket. There are all sorts of star formation regions throughout the Tarantula Nebula. You can either do the whole thing or a pocket. Anyway. Okay, so we got the size. Here's the equation. What we're gunning for is calculating that interior ionized proton density. We now have the size in parsecs. So now the tricky part, the ionizing flux. It's coming from the hot stars. You got a lot of O stars, you have a lot of flux. Ionizing flux. If you don't have as many, you have less. B stars, they produce a little bit. And it's really hard just looking at your image, figuring out which are the O stars, which are the B stars. Really what you would do is you take a telescope with a spectrograph and take a spectrum of each of these stars and determine what kind of star they are. You can tell from the spectrum. And lots of people have done this, and there are disagreements. You can go through the literature, and one paper will say, I have 5 O stars and 4 B stars, and another paper will say something different. And so we're going to use, this is the modern era, so we're going to use AI to help us here. And the reason I'm willing to do this is none of this calculation is very precise, right? We approximated the region as a sphere. That's obviously not super precise. We're measuring the size very crudely. There are going to be other things, temperatures that we measure very crudely. So we don't have to be super perfect here. And so we can trust AI to that degree. So here I am in chat. You may want to use one of the more recent versions of chat. The earlier versions tend to hallucinate a little bit, particularly with complicated questions like this. It starts making stuff up. If you use a higher version, it'll be accurate, though every time you ask the question, you'll get a slightly different response. And it's okay. We just need to be approximately correct, particularly for the most massive stars in our region. Those massive stars determine almost all of the ionizing flux. Here, before I show you the question, let's go over here to sheet 2. Here you see different spectral classes, O4 through B2. And here's the mass. O4 stars correspond to 70 solar masses. They're almost 50,000 degrees Kelvin, and they make a lot of ionizing flux, almost 10 to the 50 photons per second. As we go down to O5 stars, well, that's 60 solar masses. Not as hot, but still very hot and still making a lot of ionizing flux. And you work your way down, and here we have B2 stars. They're only 10 times the mass of our sun, only 22,000 degrees Kelvin, and many orders of magnitude less ionizing photons, because you just don't have as much out here. The cooler you go, because the exponential cutoff, you lose the UV photons pretty abruptly. So the B2 stars are barely contributing. It's like 5 orders of magnitude less than the O4 stars. Okay, so we want chat to tell us how many there are of each type. Then you take one of these regions and you type in the number of each of these classes of stars. Like here, here's one. It says there's 1 O4 star. So 1 times 8e to the 49 is 8e to the 49. There are 2 O5 stars. 2 times 3 to the E49 is 6E49, and so forth and so on. Down here, it says there are 40 B1 stars. That adds up to something times 10 to the 46, which doesn't even register compared to the 49s. So you can be really inaccurate down here, but you want to be accurate near the top as much as you can. So here's one way you can phrase the question. How many stars of each spectral subclass from O4 through B2 are in the, and then you write your nebula. I did the eagle. You'd put your nebula. If the common name is kind of rare, maybe try the NGC number. And then tell it, give me your best guess in the form of a table, subclass versus number. If you don't ask for a best guess, it will wave its hand saying, well, it's kind of uncertain and different people say different things and you should consult the literature. But we're asking it for a quick result. So, even if it kind of refuses on the first attempt, just tell it again, give me your best guess. And it will go through and do the best it can. It's a quick review of the literature. It'll give numbers that are okay. And if you want, you can do Google searches and read papers and refine these numbers, but this is a first stab. Okay. In this case, it complained once and I had to tell it again, best guess, and it gave me exactly what I want. This table, it says in the nebula, I have 1 O4 star, 1 O5 star, and so forth. They increase in number farther you go. I'm sure if I asked it again, I'd get slightly different results. But again, slightly different's okay. You can ask a couple times and average them, whatever you feel best with. Okay. You stick it back into one of these tables, and it will sum it all up, giving you the ionizing flux. Like this one here, 2 times 10 to the 50 is what they got. Go back to the first page and you enter it. And let's see, some things like the Running Man, I think there's only 1 star driving it. Demerins, there's only 1 B star driving it, so they get lower numbers. But something like the Tarantula, they're up to 10 to the 51. They're just so many stars. We've got lots of 10 to the 50s and some 10 to the 49s. And that's kind of what you expect overall. And then you can calculate the interior density using this equation. R sub S is in parsecs. N sub star is in inverse seconds. Again, be careful with the fractional exponents. When you type this into a calculator, you got to put that in parentheses or just convert to, this to the 1/2, this to the minus 1.5. I'm sorry, this to the 0.5, this to the minus 1.5. avoid the fractional exponents if you're not accustomed to doing these kinds of calculations. Okay, then you get densities. Now, in star-forming regions, the density of clouds anyway, forget star-forming regions for a second, just clouds out there in space, they tend to be between 100, so 10 to the 2, and 10,000 or so, 10 to the 4. Now, in the star-forming regions, it may be a little bit lower density. They start out at that density, but they've heated this gas and the gas has expanded. And so the densities may be a little bit on the low end of this range. You can see my students came up with things in the tens, some of them in the hundreds. Some of them are less than, this one's less than 1. But nothing really above 1,000 or 10,000. So it's on the low end. It's because these regions have, because they're hot gas, they've expanded and their density has gone down. But these are the interior densities. That's our first density that we're calculating. Okay. You all still with me? Now, this course requires a wide variety of skills. Some members of your team are going to be great at digital art and not great at physics and math. And hopefully you built a diverse team and you have someone on your team who's good at physical calculation. And they're going to be your leader. They're not going to do it for you. Everyone has to do this, but they will be your leader here. Okay. Now, the second calculation is for the outside density. And we're going to do a lower limit. It's probably not realistic, and an upper limit that's probably pretty close to realistic. Okay, let me go back to the doc cam. Get a fresh sheet of paper here. Okay, let's remind ourselves what's going on here. We got stars. They've created this H2 region. And in here, we just calculated the density of ionized hydrogen, density of protons. So this is ionized. And now we want to calculate the exterior density. Density of H sub 2. So the notation's getting a little tricky here. Roman numeral 2, that's ionized hydrogen. The kind of regular 2, Arabic 2, this means diatomic hydrogen. So this is neutral, cold hydrogen. The 2 atoms have come together and made a double. Okay. So this is molecular. Molecular. There we go. Okay. Now, initially, it's really easy. Initially, the density of that outside molecular gas is the density of the interior gas that you just calculated divided by 2. Why? Well, before the stars turned on, it was molecular gas in here. Each particle had 2 protons because the hydrogens were stuck together. Then when you ionized it, knocking off all the electrons that held these 2 hydrogens together, the protons are free. So the density got twice as high in the middle compared to what it was. So you take that interior density, which you just calculated, divide by 2, and that was the density, the number density, number of particles per cubic centimeter before the ionization. So ionization doubled the density. So to calculate that outside density where it's not ionized, you just take that and divide by 2. Come back down here. You can see the exterior density. It's a lower limit. You just take the interior density, divide by 2. Easy. But the H2 region won't stay in this state for long. Now, as we already said, it's hot in here, it's cold out here. And what does hot gas do? It expands. So this is going to expand. As it expands, The interior density goes down, which means the exterior density will be larger. Okay. So it expands, and it expands until pressure equilibrium is established. How long does this take? It takes about 1% of the driving stars here, 1% of their lifetime, to create the H2 region for it to expand into pressure equilibrium with the outside gas. So that means of the star-forming regions we looked at, 99% of them are in pressure equilibrium. So this lower limit density is not very good. We need to calculate this upper limit, assuming pressure equilibrium has been established. And that's a much more realistic density for the outside cloud. Okay, so let's derive this. We want the pressure of the inside H2 region to equal the pressure of the outside molecular gas. And I know that notation's confusing, H2 and H2. Just remember which is which. H Roman numeral 2, that's referring to the inside hot ionized gas. H subscript 2, that is molecular, that's the outside cooler gas. Now, this inside pressure, the pressure inside the H2 region, it's coming from both the protons and the electrons. So let's break that up. We have the pressure of the protons on the inside plus the pressure of the electrons on the inside will come into equilibrium with the pressure of the outside gas. That's when the expansion will stop. Okay? Now we use the ideal gas equation. You came across it in high school chemistry. If you took chemistry in college, you saw it. Pressure is NKT. Pressure is number density times Boltzmann's constant times the temperature. So the pressure of the ionized protons in here is equal to the density of the ionized protons times Boltzmann's constant times the temperature of the inside region, plus that of the electrons. So the density of the electrons, Boltzmann's constant, temperature of the inside region. Then out here, we have the density of the molecular gas, H sub 2, times Boltzmann's constant times the temperature on the outside. Okay. Well, Boltzmann's constant cancels. And we can again use that same trick. The density of the protons on the inside is the same as the density of the electrons on the inside, because it started out neutral. So when we ionized it, we have as many protons floating in that volume as electrons. Their density is the same. So we can write it like this. NH plus Ne times the temperature on the inside. It's the density of the molecular gas times the temperature on the outside. And these two we can replace with 2NH plus, because the densities are the same. We'll just replace it with 2 times the proton density times this equals this. Okay. Now we know this. We know the density of the protons, the ionized protons on the inside. We want to know the density on the outside. So solving this, we get the density of the molecular hydrogen in the outside undisturbed cloud is the density we already calculated times this ratio, 2 times the inside temperature divided by the outside temperature. Okay. Again, we already have this. We just need to know the temperature on the inside and the outside. Near the boundary, that's where pressure equilibrium is established. So near the boundary. This we can read off our image. Let me put my image back up for a second. On the inside, we have hot gas. Those are the narrowband layers, H alpha, S2, O3. Whichever one is strongest out here in the outskirts. That's going to tell you something, because each of those gases, they only emit light within certain temperature ranges. Put up the dot cam. So if you want to know the temperature of the inside, depends on what you see. H alpha, it glows from about 5,000 to 10,000 Kelvin. So on the inside of the boundary, if you have a lot of H alpha there, then the temperature there near the boundary, but on the inside of the H2 region, is somewhere between 5 and 10,000 Kelvin. Probably on the lower side. The farther you get from the central stars, the cooler it tends to get. So you may use something like 5 or 6 or 7,000 Kelvin there. Okay? Or you might see S2 out there in the outskirts. It emits from about 8,000 to 15,000 Kelvin. Or you may see O3, which is 15,000 to 40,000 Kelvin. So it's all about what you see in the outskirts near the boundary. I'll put my image up again, right around here. And in this particular image, and in most of your images, you see a lot of H alpha there. So something between 5 and 10,000, perhaps a little bit on the low side, is what you'll use for the interior temperature near the boundary. Okay. That goes here. So to finish this pressure balance calculation, we just need to know the temperature on the outside of the boundary. So near the boundary, but on the outside. And this is where the dust layers are shining. You see the orange here and the blue. That's mid-infrared emission due to dust outside the ionization region. So in the cloud, the neutral cloud surrounding it, it's a lower temperature out there. And the dust is glowing at that temperature, thermal emission. And so we're going to make use of the presence of those layers in our image to ballpark a temperature for the exterior gas and dust. Okay. So what do we have? Temperature for the molecular hydrogen depends on what you see out there. If you see Spitzer 8 micron, it's going to imply a particular temperature. What else could be out there? We have Weiss 12 micron. We have Weiss 22 micron. And we have Spitzer 24 micron. Those were the layers we tested. So again, it's thermal emission out in the mid-infrared. And to do this ballpark calculation, we're just going to assume it's near the peak of the black body spectrum. And grab this figure again. Here's the thermal spectrum. And, we're observing in the mid-infrared, somewhere out here. If we assume it's near the peak of the spectrum, we can calculate the temperature of that dust and hence the temperature of the gas it's mixed in with. So thermal spectrum, there's a relationship between the wavelength at which the peak occurs and the temperature of the gas. It's called Wien's law. I'll write that right here in the little bit of space I have left. Again, I'll just draw the thermal spectrum. Here we have log intensity. Here we have log frequency. Space, it looks like that with the exponential cutoff. We're talking about this frequency, which corresponds to a wavelength lambda. And the equation, the wavelength of the peak in microns is 2,900 Kelvin divided by T. Or if we flip this around, the temperature of that exterior gas, temperature of the molecular gas out there, is going to be at least roughly 2,900 Kelvin divided by the wavelength in microns. Okay. So again, looking at my image, I have a lot of Spitzer 8. Here I am at the boundary, and I see a lot of Spitzer 8. So assuming that's near the peak of the thermal spectrum, I use my equation. It's also written on the sheet here. Spitzer 8, that's 8 microns, so 2,900 divided by 8. So let's look at the table. Here we have the lower limit on the exterior density. Now we're calculating the upper limit, the more realistic measurement, assuming pressure equilibrium. In this column, you're going to list the narrowband emitter on the inside boundary. It's mostly H alpha. I should say, in some cases, you may not see anything. And that just means that the temperature on the inside boundary was less than 5,000. Remember, H alpha emits from 5 to 10. If you don't see any of these things, it means the temperature is less than 5,000. In that case, you're going to calculate a limit. But most of these, we have some emission, mostly in the H alpha. That's implying a temperature in the 5 to 10 range, perhaps on the lower side. So we see a lot of temperatures below 10,000. Okay. And then what band do you see on the outside of the boundary? What mid-infrared band? And we see a variety of options here. And they're calculating the thermal temperature corresponding to that wavelength, assuming it's near the peak of the black body spectrum. And often it's between 1 and 300, depending upon which wavelength you're using. That's what we see here. And once you have that, you can calculate the exterior density by this equation here. Here it is on the dot cam. The interior density of ionized protons that you already calculated times 2 times the interior temperature, which is 7, 8, 9, 10,000 degrees, divided by the exterior temperature, typically 1 to 300 degrees. So you're going to get a big boost. The density of the outside cloud is going to be a lot higher and its temperature lower. The density of the inside H2 region will be lower, but its temperature a lot higher. And that's what gives you pressure balance. Let's see what my students got for the exterior density. Again, it's an upper limit, assuming enough time has passed that you're in pressure balance. But you only have to go about 1% the age of the star for this to take form. So most of the time, this will actually be the exterior density. And I said, these clouds tend to be between 10 to the 2 to 10 to the 4. And we see a lot of things above 100, a lot of things up in the thousands, some things in the low tens of thousands. So this seems to be working out. So that's great. So we've taken our pretty picture, and now we've done some pretty serious physics. We've read temperatures off the image, both inside and outside the H2 region. We measured a size, and we calculated densities, both inside and outside. And those outside densities are matching expectations. And in the next video, we're going to take a look at those inside densities, Okay, that's it for this video.